In this video, we are going to cover the power method for finding eigenvectors and eigenvalues. Um, we're actually only going to find something called the dominant eigenvector, or sorry, dominant eigenvalue, just meaning that the absolute value of this eigenvalue is bigger than the absolute value of any of the other eigenvalues. But before we start coding this technique, I want to kind of show what's going on kind of behind the scenes. Okay. And so, is what I'm actually going to do first is actually find that dominant eigenvalue and its corresponding eigenvector, but not using the power method. We're just going to use eig here. And our outputs are going to be v and d. And let me just hit run so that I can more easily explain what v and d are. So the first column of V is the first eigenvector, and it corresponds to the eigenvalue in the upper corner of D. All right, and then the second eigenvector will be the second column of V, and its corresponding eigenvalue will be this minus 1.8730. Right, well, the dominant one is and by one, I mean dominant eigenvalue is this 5.8730. So we're going to actually be working with um, the first column of V. That's going to be the eigenvector we want. Okay. So what I'm actually going to do is I'm going to plot it. And remember, when you work with a vector that's in that kind of, IJ format, or as you maybe saw in calculus, maybe using these symbols here, okay, right? Those vectors start at the origin is what I'm trying to get at, right? And so similarly here, I'm going to start my vector at the origin, meaning that the first point for x and for y are going to be 0. And then the second value is just going to come from v. So I want that first value of v for the x value of the endpoint of our vector. And then the y point for the end of our vector will come from v of, and we want to be in row 2, column 1. There we go. And let's do a couple other things. Let's make this line width a little bit bigger. Let's maybe just make it 1. And I actually want to add one more thing. Let's give this thing a color that we can remember. Let's make it red. Here in a moment, we're going to have a bunch of other plots. Okay, well, all on the same plot, okay, but a bunch of other vectors. Okay, so here's our vector. Um, now, the question is, well, what's the significance of this eigenvector other than that it is an eigenvector? Okay. Well, we're going to find out. Okay, but I'm going to set our axes here as well. I'm going to just say 0 to 10 in the x and 0 to 10 in the y. There we go. And I'm going to use hold on because we're going to put in some more plots here. Okay. So the idea behind the power method is what happens when you apply the matrix A to a vector repeatedly. Okay. And so we're going to find out here. You can actually prove this mathematically, but I think it's much easier to understand visually here. So let's call this iteration 1. Okay. And is what we're going to do is we are literally going to take A and we need to multiply it by something. Okay. Now, you can literally choose a random vector here, but there can actually be bad vectors that you could choose as the initial one. Let's see here. And maybe we'll talk about here in a little bit what it would mean for it to be a bad vector. Okay? Or actually, I can say it now. We want this vector to have some component in the direction of the eigenvector. Okay, which is actually a pretty easy task to accomplish. So if you see that this isn't converging, maybe mess around with that initial guess here. I'm going to call this x0 since this is our first guess. Maybe what the eigenvector might look like. I'm going to multiply this by x0, and I'm going to call this x1. Right? And so when I do a times x0, it's going to give me another 2 by 1 vector, just like x0. And actually also just like our eigenvector, v that we're working with. Okay. And then by v, I mean the first column of v. And now let's plot this. And so this is going to look very similar. This is a vector. We want it to start at 0. But now it's going to end at x0 of 1. And, or actually, I take that back. How about x1 of 1 and x1 of 2? Okay. Right, the second value of x2 is going to be the y value, or of x1 is going to be the y value. The first element of x1 will be the x value. All right, and let's do all the same stuff here, all the same settings, other than we probably don't want it to be red. Here we go. All right, well, let's plot it and see what this new vector looks like that we got from just applying a to really a random vector. Okay, so, well, this one happened to be red too. Maybe I'll make it blue. There we go. So you can see the blue one is this longer one. And actually, as we continue to iterate, they're going to get longer. But you can actually already see these two things are pretty close. Okay. And if we keep iterating, the new vectors are going to be closer and closer to being in line with the eigenvector. Okay. Let's just see that that's true. We'll call this iteration 2. Um, we'll calculate x2 based on, if I can type in a 2, based on x1. Again, we're applying a now to the previous one. So again, we're repeatedly applying a. And then I just need to change all these to x2s. All right, and let's hit run. I made this one blue as well. Maybe I'll switch its color to green. Okay. And now if I zoom in, you can see that the green one's actually really close to the red one already. Okay. And remember, eigenvectors are not unique. An eigenvector, or I should say, um, when we do have a eigenvector, it can actually take on any length. The important thing about the eigenvector is what direction it's pointing. And so again, as you can see, we're getting closer and closer to pointing in the same direction. But let's do one more iteration just to see how good this did for 3 iterations. So change this to x3, this to x2, and then these last 2 to x3s. And let's maybe make this last line black here. All right. And so you actually can't even see our red line right now, but let's zoom in a little more. Okay, and so you can see that that black line, our last value, is really close to the eigenvector. So it actually ends up that if you repeatedly apply a to a vector, that it's going to approach the eigenvector that corresponds to the dominant eigenvalue. Okay. And so that's precisely what's happened here. Right now, if we want it to look the same as the red one, we can make an easy little fix here. We can just make these all unit length. So one thing I didn't mention is the first one I chose was of length 1, that vector 1 comma 0. And the other thing I didn't mention though is that v here, actually the first column of v and the second column of v, both of those eigenvectors have length 1. the eigen function gives you your eigenvector as a unit vector. Okay, so let's try to match it up with that. So all I'd have to do here is take my x1 and divide it by its own magnitude. Okay, and so if you use norm, this is going to give you the, I'm going to divide it by the norm of x1. Um, if you use norm without any settings on it, it's going to use the typical norm, your Euclidean norm. Okay, and I can do the same thing down here with x2. I'm just going to copy and paste these and change all the subscripts to twos. And we'll do that with x3 as well. And actually, I'm going to adjust the axes here a little bit. So we're only going, or these are only of length 1. We don't need to go out very far in the x or y. Okay. And so again, as you can see, the red and the black one are the closest. If we keep iterating, it'll keep getting closer to that red one. Okay. Now, this is actually pretty much the algorithm for the power method. You can see we're getting closer to that eigen vector. Okay. So is what we're going to do here in a minute is we will we're going to start coding this, and then we'll explain how we'll find the uh, eigenvalue rather than just the eigenvector. All right, so let's get this started. Okay. So I'm going to get rid of this stuff here because we don't need most of it anymore. The only thing I think I want to keep is maybe our initial guess. We'll continue to use that one. So yeah, let's get this started. We're going to use a while loop. Um, I am going to actually keep track of the count. This is not really the most important part here, but this is one way that we might decide to break our while loop. And actually, this should go down here. And maybe we'll set this as 0 initially. We're going to add more to this, but for now, I'm just going to say if I is say, let's say equal to 100 will break. We will add more to this. We're going to look at the relative error of something here in a little bit. Okay. Indenting a little bit here. Where that breaks at. There we go. Okay. Now for applying a to the the initial guess. Well, let's kind of write what that might look like. We're going to want to do that above I here. So a times, and I'm going to call it x new. A times x new. And this is going to give us x new. I might change that a little bit here in a minute. So that being said, this up here better be our x new, at least for the first iteration of this. Again, we might adjust this line a little bit here in a minute. Now the problem is we are going to need an x old eventually here, and we might need a lambda old and lambda new once we start talking about the eigenvalue. Okay. But yeah, as you can see, this is pretty much just a for loop at the moment, um, where we're just multiplying a by the new value of x new every time. Let's maybe give this a run and see how it does. See if we get any errors. Although I might lower this to 20 for now, or how about 10? That'll be probably plenty. And so hopefully we'll get the same eigenvalue that we had right here in V. Okay. This 9 or 0.9165 and 0.4000. So X new. Let's see if we get any error messages. Okay. We did not get any error messages, but you can see that this thing really got large. Okay. Well, the one thing we haven't done yet is we haven't taken the or made it unit length like we were talking before. So we could say X new is equal to X new divided by the norm of X new. Give that another go. And this is exactly what Eig was giving us. Okay, so this seems to be working pretty well. Okay. But we also are going to want to see that eigenvalue. So I'm going to switch this over to OneNote here in a second, and we'll see how we can get the eigenvalue. Okay, so we're in OneNote now, and is what I wanted you all to see here before we talk about the eigenvalue a little more is again this definition of diagonally, or not diagonally, of a dominant eigenvalue. Okay, and so all this again is saying is that the absolute value of the dominant eigenvalue is going to be greater than the absolute value of any other eigenvalue for that matrix. All right. Now, here is actually the process we've been using on the left in pink, right? We've been applying A to some, let's say, old matrix, or applying A to some old vector, and we end up with a new one. And when we go to rewrite that new vector, we actually divide it by its magnitude, right, to make it unit length. But you can see here, this whole thing makes up xn, x new, the new eigenvector. Okay. But it's actually only this part that we're calling the eigenvector. Okay. We're not actually calling xn the eigenvector, but xn divided by its magnitude. Well, this over here is true the more iterations we do. These two things become closer and closer to equal the more iterations. Okay. And so is what I mean by that again is if this is close to an eigenvector, and this is what we're calling the eigenvector, okay, or approximating it as, these two things should be pretty close to the same, right? That's the whole idea is ax equals lambda x, okay? Right? It's just our x here is this, I want to emphasize this here, our x is just this x sub n divided by its magnitude. Okay. Now, the thing that we haven't talked about again is the eigenvalue, and it actually ends up being this. Okay? And we can show it by using this fact here that these two things are approximately the same. Okay? So we have our ax 0, or ax old is maybe what I want to call it. The idea again is if this thing is really close to the actual eigenvector, then we should have an at least approximate equality here. And I'm going to write the right-hand side of our equation down again. There we go. Okay. Now that we have that, let's move some stuff around. So I'm going to just copy this to make my life a little bit easier. But what would happen is if we subtracted by all this stuff on the right, we'd end up with this minus this is equal to, or maybe I should say approximately equal to the 0 vector. Now, if I want to do any factoring, no, there is a matrix here, but I don't have one over here. Okay. Well, we can introduce that pretty easily. Um, we could actually write down the same thing again, but with an I. So I'm going to say I times xn. Because if you multiply xn by I, you're going to just get xn again. But again, the idea is I want to factor some of this stuff. So when I go to factor, I'm going to be left with a minus the magnitude of xn times I. And then the stuff that we're actually able to factor out is what we've been calling our eigenvector. Okay? At least in our code, this is what we've been calling the eigenvector. Okay? And as we saw, it actually it is. It's getting closer and closer to it. Okay? But is what you can see, right, is the eigenvector lambda is given in this. This is the equation for finding your eigenvectors, okay? Right? Where lambda is your eigenvalue. And look right where the lambda is. It's this magnitude. So it's just the magnitude that's going to wind up being our eigenvalue. Okay. Well, let's go check this out in MATLAB and finish this up. Okay, so we've dealt with x. Okay, let's come up with lambda. Okay, so I'm going to write it here. Lambda is equal to the norm of x new. Okay. And then is what I can do is down here, since we're already going to be computing lambda, why don't we just write lambda down here? So that should do the trick. Now, we don't want to just pick the number of iterations to stop with. We'd like to see that relative error shrinking. But to compute our relative error, we're going to need either an x new and an x old to compare, which you could imagine in that situation, we'd probably want to subtract the x new and the x old, and we'd want those differences in each component to get really small. So maybe we'd want to take the maybe the maximum of that and say that it's less than something. Okay. But it might be a little bit easier if we just use the lambda because it's just a scalar, it's not a vector. Okay. And then we don't have to deal with, subtracting the components. Yeah, it'll just be a little bit easier. So let's get this started here. I'm going to say, I know we don't have it in here yet, but I'm going to say lambda olds is going to get subtracted from lambda new. And we're going to divide this by lambda new, and we'll multiply this by 100. Okay. So there's our relative error. Now, for breaking, maybe I'll switch this back to 100, but I'm going to say, or EA is less than, and let's just say 0.001. Or maybe we'll add one more zero in there. It'll be kind of up to you if you're using this, what you want to set EA to be, or the stopping criterion to be, and what maybe you want I to be. All right. Now, we don't have lambda old in here. So is what we could do is up here at the very top, we could say, well, how about we let lambda old become lambda new? All right. And let's see. If we do that, right, we will get that lambda old is equal to the old lambda. And then our new lambda will be calculated right here. Now, if we do this, there is an issue in that we haven't defined lambda old here yet. Okay. Well, you might have to adjust lambda old here a little bit because if you choose the actual eigenvalue here, then your relative error could wind up, yeah, your relative error could end up being zero right off the bat, and I question whether that would make things run nicely or not. We might have to adjust this lambda old and the x new a little bit here, okay, to get convergence and to get this to work properly. So let's give this a run, but we do want some outputs here. So we said x new, right? This is the eigen value or eigenvector, and the eigenvalue is going to be equal to lambda nu. And actually, I don't want to suppress those. I want both of those to appear here. So let's hit run and see if our results match what we had with eig. Okay. So we do have an issue here. Lambda new, unrecognized function or variable lambda new. And it says line 14. Ah, I see. That's because I need to make this one up here lambda new. And it will very soon become lambda old. In fact, as soon as we enter the while loop. Okay. Now we have an x new that's an issue. So x new, maybe we should call this, um, let's see. We could definitely call this x old. That would fix it at least for the first iteration. Um, mm, yeah. I'm just thinking here. This x new, again, that shouldn't be problematic. Oh, I'm missing an underscore somewhere. Yeah, in line 16, I need my underscore. There we go. Right, and I probably have another typo here. Um, yeah, divided by lambda somewhere. Line 17. This one should be divided by lambda nu. There we go. Okay. So this is the eigenvector in the eigenvalue that I was giving us. Now that we fixed the little typos in there, it actually ends up that there are kind of some modifications to this technique here, the power method, where you can actually go and you can find the rest of the eigenvectors and eigenvalues. But this is all we're going to do for this. I don't want to go into that much detail. Um, we'll just call it good here with finding the dominant eigenvalue, its corresponding eigenvector. And for everything else, if we're not looking for that dominant eigenvalue, you can just use eig. Okay. But that's it for this video, and thank you all for watching.